Good morning.
Good morning.
Thank you. My name is Cassandra Alvarado. I'm Assistant Dean for the School of Undergraduate Studies, and I'm delighted to welcome you to the Making Decisions with Data kickoff. This is sort of a two-part event, the first of which is our fabulous talk by Dr. Eric Mazur, who I'll introduce in just a minute. And second is really to introduce you to a resource developed by the School of Undergraduate Studies with support from the Texas Higher Education Coordinating Board to help educators make decisions with data. This new online resource, which we'll unveil at the end of our talk today, is really designed to help folks here on campus and across the state understand the value of data in making decisions. And we're really excited to kick off this event with Dr. Eric Mazur. We're thrilled to have Dr. Mazur back on campus. Eric is the Balkanski Professor of Physics and Applied Physics at Harvard University and is the Area Dean of Applied Physics. He's an internationally recognized scientist and educator, and his work has inspired change in teaching all around the world. I'm pleased to say that Dr. Mazur has inspired a change in my teaching and inspired a change that has helped me use data to make smart decisions about what's happening in my classroom and what's happening in the programs that I support across campus. And it's because of his work that we're delighted to have him here today to give us his talk on the scientific approach to teaching. Dr. Mazur.
Thank you very much, Cassandra. I think you're giving me too much credit, really. But it's a great pleasure to be here and to be talking about something that is very dear to my heart as a scientist, namely talking about the role of data in the decisions we take about teaching. And it's particularly fitting that there's this wonderful project here on campus that will go live, I hear tomorrow, right? That's the plan, at least, this website here, that shows how you can use data to inform important decisions, to take important decisions about your teaching. And if you haven't gotten enough of me today, you'll be able to see some videos about the role of data in my classroom and what got me to change my approach to teaching, essentially. And I hear we'll see more of that after my presentation. Okay, so those of you who've heard me speak before have seen this picture that's in the background. I use it in all my talks. It's a very old picture of me teaching my pre-med physics course. This picture was taken BC, before computers. See, I'm using an overhead projector. And the message I've been hammering on relentlessly is that this activity here, which ironically I'm doing in front of you right now, lecturing, is basically focusing on the transfer of information. Now I want to show you something about data right off the bat before I get to the actual substance of my talk. Usually when I show that picture, before I show them this one with the arrows, I ask people to, in a few words, tell me what is happening in a standard lecture. And you hear things. And the words that I don't want to hear are teaching and learning. So you hear people saying watching, talking, pointing, and so on. It takes a while usually before people come to the transfer of information. But there are invariably always a few people who will say sleeping. And it's actually closer to the truth than we might think. Many years ago, the French author Albert Camus said, some people talk in their sleep. Lecturers talk while other people are sleeping. But recently, there have been data that have been collected at MIT to back up this claim, which are pretty interesting. It was actually not an educational study. It was a maybe we should turn down the volume a little bit because there's a little bit of feedback. The paper in question, I'll show you the DOI in a second, and if you are unable to quickly write it down, you can always download my slides and find it. It was really a paper explaining how to measure neural activity in a very non-intrusive way, using a wearable wrist sensor that measures electrodermal activity. And the paper basically talks about the electronics of that sensor and also shows the correlation between the electrodermal activity and an EEG, which is not that surprising, right? Neurons are connected to the brain. The great benefit of these sensors is that you can wear them around your wrist and then go about your daily activities while the sensor collects the data, and then after a week you can download them and analyze them. It's kind of hard. This work, by the way, was done in the group of Ross Picard at the MIT Media Lab. You know, and it would be hard to have somebody walk around with EEG electrodes on his skull, right, for a whole week. Maybe at MIT you could do it, I don't know, but but anyway, the paper has one figure that shows the neural activity in the brain of one MIT student. And they asked that MIT student to not only wear it and collect data, but also keep a logbook of the activity. So here's the trace. And you can see day 1, day 2, day 3 on the vertical. So each row is a day, and you can see periods of high neural activity and lower neural activity. And here's time, 4 o'clock in the afternoon. I don't know why the day at MIT starts at 4 o'clock in the afternoon, but anyway, till 3 o'clock and so on. And I want to draw your attention to the parts of the trace labeled class. The trace goes flat. Compare that to the neural activity during the student's sleep. In other words, the students are more asleep in your class than they are in their own beds. Now don't look at the screen, look at me. Because the answer is on the screen, I don't want you to see it. There's one activity that matches class. Guess what it is? Don't look at the screen, look at me. Watching TV, there we go. During the TV watching, the trace goes completely flat. And this, of course, is something that we've known a long time. People have done EEGs of people sitting in front of the TV, and the brain goes into a meditative state with lots of alpha waves. The reason is very simple. When you're exposed to a continuous stream of information, there's no time to think. Information just comes at you. In fact, you know, many of you may have gone to see a movie of a book you've read. And invariably, people report having more pleasure reading the book than seeing the movie. The reason is, when you read a book, you can pause and think and dream and imagine. Yes, in a movie there will be emotions, but there's no time to think. There's no time to dream. There's no time to imagine. All the imagining has been done for you, and the information is just coming at you. Likewise, in a lecture, including this one here, I'm afraid to admit, there's no time for you to think. If you start thinking, if you start daydreaming, you cannot at the same time be listening to me. And therefore, in a class, all you can do is take in the information, and if you're a note taker, you can jot down some of that information into your notebook. So I was really pleased to see these data backing up something that I think people have been intuitively feeling for a long while. Your mind is held captive by the presenter in a lecture. There's no time to synthesize the information, to make sense, to have this aha moment. Anyway, today I want to focus on a very different message. Let's not abandon the scientific approach when it comes to teaching. When I joined the physics department at Harvard as an assistant professor in 1984, there were 27 physics professors, and it was an amazing time. 6 of them had the Nobel Prize. It was a very intimidating place to be as a young junior faculty. A very nice department, though. It was a very good social atmosphere. Every Monday, we'd go out for lunch, and you know, in the faculty club, both socially, but also to discuss matters pertaining to the physics department, one of them being teaching. And in retrospect, thinking back of these discussions, it's actually shocking to realize that most of these discussions were completely anecdotal. My students learn better when I do this or that. Or my students enjoy it when I do lots of demonstrations. Fine if they enjoy it. Are they actually learning better? There's one quote which I'd love to show you, which I also love to rub in the face of my colleagues when they revert to anecdotal evidence. It's by Schulman, former president of the Carnegie Foundation and professor emeritus at Stanford. He once said, "The plural of anecdote is not data." Well, it's shocking to admit that most scientists are completely anecdotal when it comes to talking about teaching. And I think this is why it's so important to have this project here on campus to collect data, use data, look at data to basically improve the decisions we take in our approach to teaching. So I'm going to show you 3 distinct little projects. Some of you may have seen the data I have collected that got me to change the approach to teaching. Since I've spoken on campus several times about that, I thought I was not going to rehash those data one more time. If you've not heard them before, you can go to YouTube and see a presentation I gave entitled Confessions of a Converted Lecturer, which showed the data that got me to abandon lecturing. Except when I talk to other people. You see, we all really love hearing ourselves talk, and I miss lecturing, so I'm very happy that Cassandra invited me to come and lecture to you here. Anyway, so I'll talk about 3 different projects that we've carried out, which some of them are more science-related, and of course they're all in the context of science because I happen to be teaching science courses. But I think the idea behind it, collecting data, taking decisions, are transferable to other disciplines, and maybe even some of the conclusions might be valid for your own discipline. One is gender issues. The next one is lecture demonstrations, which, as you may know, in science is very important. My courses used to include lots of demonstrations. I'm an experimentalist, so to me, there's no better evidence than seeing it happen in front of your eyes, or so I naively thought. There's another talk, which you can also find on YouTube, called Visual Illusions, How the Mind Tricks Us, which goes into somewhat greater depths on the lecture demonstrations if you are interested. And then the last part is something that I think is extremely hard. It is extremely important, namely the role of confusion in learning. I was just the last week interacting with a young writer, Jamie Holmes, who is writing a book on the role of confusion in education. I'm very much looking forward to that book. So let's start with the first one, gender issues. The thing that's got me to start my approach to teaching is the force concept inventory, which is an instrument that measures students' understanding of the concept of force. Now, in a typical physics course, force is one of the first concepts you teach in week 2 or 3. And after that, everything else builds on top of that concept. Work, impulse, momentum, energy, and so on. They all are related to the concept of force. If you do not understand force, it's very hard to make sense of these other concepts. Well, the concept of force is embodied in Newton's 3 laws, which are sometimes called Newtonian mechanics. And the force concept inventory basically tests whether a student conceptually understands the idea behind Newtonian mechanics. Well, it turns out that in a traditionally taught course, including my own, there's not much difference whether you give the force concept inventory at the beginning of the course or at the end of the course. Instead of becoming a Newtonian thinker, most students remain an Aristotelian thinker, connecting force to velocity rather than force to acceleration. And when I discovered how poorly my students did on this force concept inventory, I decided to change my approach, and I dramatically improved the performance. But one thing that was kind of interesting and stood out, these are actually data not from Harvard, but from the University of Minnesota, was that there is a statistically significant difference between the performance of male and female students, as you can see here. These are post-test scores. This is at the end of the term, the University of Minnesota data. Now, this is the end of the term, and this just tests the understanding of the concept of force. Look where we are in an absolute sense. Forget about the gender gap for a moment. Only at 50%. Okay? Means that we have to make quite a bit of advances in our approach to teaching. But anyway, I'm not going to focus on the overall value. I'm just going to focus on that difference between the male and the female scores. So the gender gap, which is somewhat over 10%, here are the data for the University of Minnesota. Let's compare to some other institutions. When I saw those data from the University of Minnesota, I thought I should go back and analyze my own data. I'd never separated them into male and female data. I just had kept those data. And it turned out that for the two different types of courses that I taught, a higher level and a lower level physics course, in the middle there, the two middle bars, the gender gap was also about 10%. And at Worcester Polytechnic Institute, which is just outside of Boston, we also have, which is a small engineering-oriented school, we have a similar gap. So three very different environments, an Ivy League school in the middle, a large state school on the far left, and a small engineering school on the right, a gender gap in all of them, which is on the order of 10%. So the first question I'd like to pose is, what causes this gap? And I have the benefit, like all academics, to have sabbaticals. And whenever I'm on a sabbatical, I try to get data in the institution that I visit. So shortly after this became of interest to me, I was spending some time in Belgium at a university which I promise not to reveal the name of. And in Belgium, they speak Flemish, which is very close to Dutch, which is one of my mother tongues, because I was born in Holland. So we took the FCI, translated it in Dutch, and I convinced one of the faculty members in the physics department to administer the FCI to the introductory physics class students in Belgium. Now, I was educated in Europe, and when I saw the problems with the FCI in the US, I attributed it to what happens in high school. Most students in the US only get 1 year of physics, maybe at most 2 if they take an advanced placement course. Back in Europe, in high school, I had 5 years of physics. I had much more time to assimilate all of these ideas of Newton's laws. So I attributed it to the problems in high school that we had such low performance. So I was kind of convinced to see that in Belgium, which is not that different from the Netherlands, students would actually do significantly better than students in the US. Boy, was I wrong. It shows how you cannot trust your intuition. And the mistake I made, of course, is the mistake we all do, namely to project our own experiences on the world around us. I did well, probably in spite of the way I was educated, not because of it. And we're all different. We all have different interests. So, it doesn't work. In any case, the students did so poorly that the dean asked me to never disclose these data. So I'm disclosing them to you without telling which university it is. I never published the data either, in part because N is relatively small, the number of students, a few hundred. But more importantly, and more pertinent to the subject of our discussion here, is that the gender gap was huge. It was actually twice as large as the gender gap at Harvard. Later, I was on sabbatical in Taiwan, at Taiwan National University, which is their flagship university in Taipei, Taiwan Dashui. And my first 4 graduate students all became professors there. So one of my first sabbaticals I actually spent there. They invited me to come there. They were young professors, either in the electrical engineering or in the physics department. I showed them the results of the FCI at Harvard. They became excited about it. I said it would be good if we could gather some data on student performance at Taiwan National University. And but they didn't teach any of the introductory course, so they had to go to their more senior colleagues to ask if we could administer the FCI to those students. Well, the more senior professors looked at the FCI and they said, this is crazy. You know, we can't give something that is this simple to our students. I would say, well, look, I'm giving it at Harvard and students don't do that well. Well, instead of believing me, what happened was that Harvard's reputation in their eyes went, plummeted down. Whatever I said, I could not convince them to administer the FCI. This was probably about 20 years ago. Now they're actually administered and discovered that, yeah, there is a problem. But anyway, so I couldn't give it at Taiwan National University. But near Taiwan National University is Taiwan National Normal University, which is a university that focuses on the training of teachers. And there they were very interested. So they translated the FCI in Chinese, and then I had my graduate students translate it back from the translated version into English to make sure that we didn't lose any subtleties. We gave it, and two things stood out. The students there did as well as the Harvard students. So the overall performance, which was better than the ones in Belgium, and better than the ones at the University of Minnesota, not surprisingly because it's, the students are selected. But Taiwan Normal University is not a selective institution. But more importantly, there was no statistically significant gender gap. So I would have loved to be able to investigate what the causes for that was. I don't know because, I didn't stay there long enough and I didn't follow up with additional studies. So here, I'm unfortunately venturing a little bit into the anecdotal regime here. But one thing that stood out was that in Belgium, there was absolutely not a single female faculty member. It was a completely male-dominated environment. At Taiwan Normal University, about half the faculty was female. At Harvard, we have maybe 20% female faculty. So there's at least a correlation, which doesn't establish a causation, but there's a correlation between, faculty gender and student performance. But clearly, from a purely cognitive point of view, there should not be a gender gap. What about the effect of pre-college education? And here I cannot connect it to other countries because I didn't have access to those data. But at Harvard, I did collect information from my students on the exposure that they had to physics before coming to college. And some have had no high school physics whatsoever, and others have had an AP course, on which, given that they're Harvard students, most of them have scored a 5 out of 5. And I actually did this because I was on the AP development committee, and I thought I would love to see how AP correlates with students' understanding of physics. Well, there is some correlation, but it's pretty disappointing. Notice that the students who have had no high school physics whatsoever, and who guess on quite a few of those questions, do worse than those who have a 5 on the AP, but the ones who have a 5 on the AP are still below the cutoff of a Newtonian thinker. So that tells you something about the AP courses. These are the scores for the female students. Here are the scores for the male students, and notice that the gap persists. Even at the highest level, it is statistically significant. But the picture becomes even worse when you look at the numbers, because you see that there are far fewer female students who persist to the AP level. So here's the gap, and here are the numbers. It might be hard to read, but there's about equal numbers that have not had any high school physics, around 18, 110 who have had high school physics, but then there are half as few women as there are men who have taken high school physics course. Okay, so nothing I can do about this at the input end, because this was all on the input end of the course. The question is there something that we can do in the classroom to rectify this situation? And I had been reading that a collaborative environment, as opposed to a competitive environment, one in which there are many verbal exchanges, actually benefits female students. Well, that sounds like peer instruction. For those of you who don't know peer instruction, it's an instructional approach I developed in the early 90s to teach large classes interactively. Rather than teaching by telling, as I'm doing to you now, I teach by questioning. The information transfer takes place outside of the class. Students either read the book or they watch a videotape of a lecture that I've given before. And then in class, I teach by questioning. I'll walk in, I'll ask a question. I let students think in silence for about a minute. They commit to an answer. This can be done on a piece of paper, or it can be done with a clicker, or it can be done with a web-enabled device. And then I tell them now, try to find a neighbor who has after they've committed, try to find a neighbor who has a different answer and try to convince that neighbor that your answer is right, or your answer is more valid, because I mean, there are many disciplines in which there are no right and wrong answer, but you basically have to defend your point of view. First time I did this, I had not much expectations, but what happened that very first time in my class of 250 students was complete chaos, utter chaos. They all started talking. I'd never seen that. They forgot about me in front of the classroom. And what happened was that very quickly, the students taught one another. Why? Because if you have a right balance of correct versus incorrect, or well-defended answers versus not that well-defended answers, you have many pairs of students in parallel addressing each other's specific problems, which is something that I, as an instructor, would never be able to do. Then I have them commit again. We wrap up, possibly with a few students explaining their points of view, and we repeat the cycle. So that's peer instruction. Well, as you see, it's sort of a very active instead of passive environment, one in which you're in a continuous verbal exchange with your neighbor. It's a safe environment because it's okay to be wrong. All right? You can stick out your neck and answer it incorrectly. There's no penalty for that. There's continuous formative assessment, and some studies have shown that benefits female students. So since I had collected data before I switched, as a scientist, I've always been a data junkie. So from the very first day I taught, I started collecting data and putting them in a spreadsheet. And by the time I switched, I already had 7 years worth of data accumulated that I could reanalyze. So the question is, does increasing the collaboration and the interactivity help address some of this gender imbalance at the input end? So I decided to compare 3 pedagogies. One, traditional pedagogy, which is just the tried and true, well, it's not that true, but lecture approach, which is as outdated as the academic robes we wear at graduation. Then interactive lectures, basically just changing the lecture component to become peer instruction. And then something I'll call interactive engagement plus, where not only we used interactive lectures, we made all of the other components of the class also collaborative. Collaborative homework, collaborative discussion sessions, and so on. The only part that was not collaborative was the examination. So here are the average scores for the 3 different treatment groups. Traditional on the far left, just peer instruction in the lectures or interactive engagement in the middle, and interactivity in the classroom and outside the classroom, i.e. plus, on the right. There's no difference on the pre-test. This is, the first day of class. That's reassuring. That means we have the same students in the 3 different groups. I want to remove these bars. That little triangle on the far right side gives you the average of these 3 different groups. Here are the males. There's a slight variation there, but the variation is such that it actually strengthens my arguments, doesn't weaken my argument. The red gives you the average male pre-test. So let's first see what happened to the female post-test score. So I'm going to remove all these bars, just keep those 2 little triangles to show you the average female and male pre-test scores. Here are the female post-test scores, and you can see that the female students gain significantly from each increase in interactivity in the approach. The men do too. It's not that the improvement comes at the expense of the male students. But importantly, the gap is no longer statistically significant in the last bar. So it's completely eliminated. And if you're interested in more detail, there's that paper that we published in 2006 that has far more data and gives you all the statistics and everything. And we literally have thousands of students because it was a multi-year study. This is actually not in the paper, but I can show it to you. Who are the low-gain students? So what I'm showing here on the horizontal is the pretest score. So for that one student whose data point is shown here, we had a pretest of 70%. That's why the student is at 70% on the horizontal scale. And a post-test of 90%, which means a gain of 20%. The maximum gain would have been 30, and the data point would have been on that diagonal line. It's impossible to have a data point above that diagonal line because you can't go over 100%. So if you take all of the female students, that's where they are. Take all of the male students, there they are. And if you look at who lies in the lower, below the median, you see that there are more women than men. This was a traditionally taught class. After switching the approach, you see that all the data points move up towards that diagonal line, which means that everybody gains. But if you now look in the lower third or so of the course, you can see that there's no overrepresentation of women there. So it really addresses, it really corrects the gender balance significantly. So points to keep in mind from this first part is, one, the gap at the input end, at least here in the US, comes, is cultural, and it comes from whatever happens in middle and high school. But even if that's there, I mean, I'm not saying we shouldn't address that, but that's unfortunately outside the realm of my influence. But even if that's there, we can do something at it relatively easily by improving the interactivity in the classroom. I'm happy to take some questions now because there's going to be a switch now to a totally different subject. So feel free. I do want this to be a little bit more interactive than it's been so far. So yes, I'll repeat the question.
What do you do if the classes in the interaction section converge on the wrong answer?
So the question is here, what do you do if the class converges on the wrong answer? So this would be an assigned subject where there is a right or a wrong answer. I can show you data. I mean, it's interesting to look at data. Maybe I should actually do that. We have an hour and a half, so I have some time to show you some data, talks, and design. I'm gonna show you some data that actually show you what happens to pre to post, and it's probably more convincing than just trying to argue with words. Here we go. So here I'm going to show you for one semester worth of questions asked in class, the percentage correct before discussion versus the percentage correct after discussion. So here, for example, is a very good question. This question initially got 61% correct and 95% after, for a gain of 34%. So good questions are, as far as possible, up from this diagonal line. Questions that you were referring to are the ones that lie below this line. So let's first look at a whole semester's worth of data. There they are. So each dot there is one question in one of my classes. The reassuring thing is almost all data points are above, and some very significantly above. The next thing to note is that there's sort of a trend there, right? The gain is the largest in the middle. It's not that high at the high end on the right, which is not that surprising, right? Because that means before discussion, most students already had the right answer, right? And then it's also low on the low end, but that's because there aren't that many students who have the right answer, so when they talk to each other, the right ideas don't spread. Yes, two students with the right answer can still, by talking to each other, you know, in sort of a constructivist manner, poke holes in each other's reasoning and then get to the right answer. That does happen, but it's less likely to happen when one student can explain to another, right, in his or her own words, where the thinking is wrong. So I basically eliminate the questions typically that lie outside of this range, which I don't know the first time I teach a new class, because I don't know. And, you know, occasionally the class converges on the wrong answer, as you can see for a few of those data points. Often that is because there's an ambiguity in the question. There's something that I haven't articulated the right way, and the students draw another conclusion than I had intended them to conclude. For example, you know, I may make a drawing, and in my mind, it's a top view of something, but in their view, it's a side view, and the gravity is down, and oh, they take gravity, and I find out during the discussion that that's what they're thinking. Or without articulating it, I expect them to ignore friction, and they do not ignore friction. If you don't ignore friction, then what is right and wrong is very different than when you do, right? Which actually has taught me one very important lesson. We tend to think that in science there are always right and wrong answers. But what's right and what's wrong is predicated on assumptions which might not always be articulated. Anyway, so yes, sometimes that happens. Sometimes I make mistakes. I have to tell you this little anecdote. I ask my teaching assistants to come to class. I demand that they come to class, because I want them to be part of this discussion. When students talk to each other, I want them to go around and listen in, find out how the students are thinking. One day, I think we were talking about rotational dynamics, I was asking a question, and I was looking at the answers come in on my screen, and most students got answer number 2, which was not the answer I wanted to see. So, you know, we were basically somewhere here on the low end, right? Sometimes you can rescue one of these questions by saying, most of you have chosen answer number 2, but unfortunately that's not the right one. Talk to each other. So that's precisely what I did. The class erupted in chaos. But the teaching assistants who were sitting in front also started to become very vocal. They started to talk. And after about 30 seconds, one of them came to me and said, "Are you sure answer 2 is not correct?" I say, "Yeah, I'm sure." So he went back and they talked again. A little later, 3 of them came to me. I said, "We really think answer number 2 is correct." I looked at my screen, and then I looked at the overhead projector, which was projecting the question, which was not on my screen. And I realized that in my mind, I'd swapped 1 and 2. So I had indeed made a mistake. But it was too late to do anything, because by then, the class had started to vote in the second round. And now most students were voting 1 rather than 2, even though 2 was correct and 1 was wrong. So I had actually pushed them to the wrong answer. It shows that, you know, authority is a dangerous thing to accept. That was kind of an eye-opening moment for me, frankly. So it does happen, but it doesn't happen that often. And in general, even in a year that I don't, this is the first year that I taught that course, that particular course. You see there are quite a few questions that are on the low end, quite a few questions on the high end. But even then, overall, the learning gains, as measured by the FCI and by other metrics, are substantially higher than those when I teach a traditional class. So I live with it. That's the short answer to the long answer I provided before. Okay, thank you for asking that. No, I need this. Okay, any other question about gender gap? Yes?
Well, I guess not about gender gap, but do you cover the same amount of material using the peer instruction method as you do as one would typically see in a traditional lecture, or are there some compromises that need to be made?
Yeah, so the question is, do I cover the same amount of material when I teach this way as when I teach a traditional way? The answer is no, I don't cover anything. But let's ask ourselves the following question. Is that what really matters, the coverage? I mean, think about it. When I taught a traditional class, I covered everything. I covered absolutely everything. The students did not even learn the concept of force. In other words, they had learned nothing. What good is it? What good is it what I cover? What really matters is how much is uncovered in the students' minds, right? So now I cover nothing. I literally cover nothing in class. The coverage in the course is not determined by what I do in the class. It's determined by what the students do in their pre-class assignment. And you may say, well, you have Harvard students, they are more motivated. Oh, no. In fact, you know, at Harvard sometimes you have a big problem because they've been selected on assessments like the AP, and I showed to you what a fallacy that really is, right? They've become very good at passing tests, but in terms of their either motivation or approach to teaching, you know, sometimes leaves a lot to be desired. So my answer to your question is, what matters is not how much the instructor covers in front of the class. What really matters is how much the students learn. And by that metric, the peer instruction approach was me covering personally a lot less material, you know, yields much better results because the students' learning gains have tripled, a factor of 3. Not 30% or so, no, a factor of 3, 200% higher. Now, you know, I don't want to belittle your question because I think it's a very important question. And some students actually, you know, just as we have our beliefs about how we should teach, so do students have their beliefs about how they should learn. When I taught my traditional class, some of you may have heard this anecdote, I used a different book to teach from than the book that I gave to the students because I just didn't want to regurgitate the test. And on my end of semester evaluation, students would just write down Professor Mazur lecture straight from his lecture notes. I'd get livid. That no longer happens because I'm not covering the material. You know what happens now? Now they write down, Professor Mazur is not teaching us anything. We have to learn it all ourselves. So, yeah, I don't cover, they cover, which I think is exactly what we want to do. But overcoming that resistance might be a problem. Yes?
Is this method as effective for teaching very advanced concepts as it is for teaching very basic fundamental concepts?
So the question is this method as effective for teaching very advanced concepts as it is for teaching basic concepts? Yes, absolutely, because we learn by doing. I wish I'd done my little survey. I often, when I give a talk on education, have people reflect on their own education first. And if you have people reflect on, if you think about what you've learned, the important skills you've learned, the things that have made you successful in your career, it's highly unlikely that you'll attribute that learning of that skill to sitting in a lecture. Because we learn by doing. We learn by practicing. And that's true at all ages, from toddler to lifelong learner. But let me give you an example. Every other summer, I teach at a NATO Advanced Study Institute summer school in Europe, in Sicily, in Italy. And the subject of that summer school is nanophotonics, which is my research in physics. What happens is there are 12 professors from around the world who each give 7 hours of lectures, and that whole thing then constitutes the summer school. The attendees are the 12 professors, a number of other professors who want to learn about the subject of recent advances in nanophotonics, and then graduate students and postdocs, on average about 70 people. And typically, I've done that now for probably 25 years. And typically, I deliver my 7 hours of lectures, and then I become a participant because the other lecturers are not always the same, and I want to learn about new things, metamaterials, you name it. And that's when I discovered, boy, it's hard to be listening to the same person for a long time. And if you lose track of the train of thoughts in lecture 2, then lecture 3, 4, 5, 6 become extremely tedious. Luckily, now, this wasn't true 25 years ago, they have wireless, so I just open my laptop and catch up with my email. But way back then, that was not possible. And that's when I thought, I should make these lectures interactive too. Now here the audience is faculty, postdocs, and graduate students, and it's a highly specialized subject like nanophotonics. First time I did it, I wasn't quite sure how it would work. I mean, you have to be a little bit more careful with the egos of people, right? Given that they're faculty, and faculty have a lot more trouble admitting that they're wrong than students. But it worked just as well, the same level of engagement, provided you give them an opportunity to address their own misconceptions in the field, they'll get engaged. That's the beauty of the human mind. We want to solve things. We want to understand. That's how we're born. We'll get to confusion in just a second, right? But we're born to learn. And somehow, in the educational development of people, that curiosity gets turned off. But it doesn't take much to rekindle it. You ask a good question, people want to get it right. So I think it works at all levels, provided you address relevant questions. Now that's less obvious, right? So in a class, I've sort of shoved this under the rug here. I wasn't planning on talking about it. But that comes also back to your excellent question. What I do is that I tie the pre-class assignment to what happens in class. And I'll show that actually in the last part of my talk, if we get there. I basically have them view something or have them read something, and I elicit the questions that they have about the material that they've done. So these are not questions that come up in my mind. No, they're questions that come up in the student's mind. In class, I'll take their questions, project them on the screen, and bounce them back at the students. Now, in the summer school, I can't do that. But one of the things I can do is observe my own graduate students and notice the traps that they fall in with their thinking, and then use those to construct activities in the classroom from. I hope that addresses your question. Let's take one more and then go on. Otherwise, I'll never get to parts 2 and 3.
I'm just curious how you sell this different way of teaching in your class. How much resistance do you encounter from the students, and how do you address that?
So the question is, how do I sell this method, not to colleagues, but to the students in my class, and how much resistance do I get? I get quite a bit of resistance. You know, resistance in part because change is hard, and because, as I said before, students have their own views of how they should learn, and they've been taught by lecturing, and they've done well, so they expect lectures. I have some students who will come to me in week 2 or 3 and say, I like the questions you're asking in class, but when are we going to do some real physics? To them, that's not, you know, the physics that they've seen in their high school courses, in their AP courses, and so on. In my book, I devote a whole chapter on motivating the students. I have to work on it. I have to show them data too. I have to say, look, and I will still get an email in week 2 or 3 of my class of a student who is livid and says, I am not paying $57,000 to learn it all myself. You should restructure the lectures, and you know, you have to go, not the clickers are fun, but you have to go through everything of the reading point by point in class, right? What I sometimes tell my students is, you know, if you want, I love lecturing. If you want, you can come to my office. I have a blackboard in my office. I'll be happy to write the book on the board, and then you can copy it in your lecture notes. Luckily, no one has ever taken me up on that. But yeah, I have to work hard on convincing them. I suggest we go on. I'm hanging out all day here, so we can find some more time to interact later. What about lecture demonstrations? Back about 15 years ago, I read a thesis by a graduate student of the physics education group in Seattle at the University of Washington, who had done interviews with students at the end of their courses. And in one of those interviews, a student describes a demonstration that she had seen, or he had seen, in the classroom. And the student incorrectly remembered the outcome of the demonstration, right? Vividly remembered it, but incorrectly. So I thought, that's curious. You've seen the demonstration. I mean, what can be more convincing than seeing how it happens? How can you remember it incorrectly? So I decided to set up a study to systematically study the effectiveness of demonstration, especially because I, as an experimentalist, love doing demonstration. In fact, I don't know how many of you have seen Walter Lewin's physics lectures at MIT. You know, my lectures were exactly like that. I would go on a fire extinguisher propelled cart and, you know, fly through the lecture hall, hoist myself up to the ceiling, do all kinds of things, you know, fire a powder-loaded gun at a suspended monkey high up. I mean, all kinds of things, you know. I mean, it was like Hollywood show. And there was, of course, the entertainment part of it, but I was sure that there was also an educational value to it. So I decided during a 2-year period to divide my class into 4 treatment groups, right? 1 quarter, 1 quarter, 1 quarter, 1 quarter. 1 quarter got no demo. So we didn't do this in the large lecture hall. We did this in the sections. That was our control group. Another one, we told the instructor to do the best possible job showing and explaining the demonstration. That was the observe. The next one, we had the students look at a transparency that showed a cartoon of the demonstration so that they knew what was coming. And then they had to predict the outcome of the demo, and then we had the instructor do the demo. So they looked at the cartoon, they thought about it, they predicted what would happen in a multiple choice fashion, and then we did the demo. And then the third one, we gave to the students a worksheet. At the top, there was a description of what the demo was going to do. Then they had to describe in words their prediction. Then we did the demo, and there was an area for them to write down their observation. And beneath that, they had to check a box. My prediction does check or does not check correspond to my observation. And then we gave them a few minutes to talk to each other and resolve any inconsistencies between prediction and demonstration. So there's clear more investment of time, right? Between no demo and demo, there's whatever time the demo takes. Between the next two, you add another 2 minutes, and the last one adds another 8 minutes in total. And of course, during the term, what we did is we rotated the modality among the different groups. So 1 week you may be in a no demo group, the next week you may be in predict or observe or discuss, and we kept rotating around. The students didn't know, well, we had IRB approval, of course, but the students didn't know which week and why we did this. So then we followed up with a free response test where we tested their memory of the observation, and also we tested if they were able to extrapolate what they'd learned from the demo to a new situation. And then complete transfer we did on exam questions by taking the same concept but putting it in a completely different context. So let me show you a demonstration. One demonstration is this loaded beam demo. You have 2 scales and a plank and an object in the middle. And the question is, what happens to the reading of the scales when you move the object to the edge? This is discussed in the context of the concept of torque. A widely held misconception is it doesn't matter where you put it because the beam equalizes the load. But it actually does, because you not only have to carry the weight of that block, you also have what is called a torque. So when you put it on one end, one scale goes up, as shown here, and the other goes down. I used to just do that demo, and the students would write down a few things and so on. So let's first see what the follow-up question is on the online test. On the online test, we made this numerical, so we showed 10 and 10, and then we asked them to fill out the question marks there. What happens when it's all the way at one end, which is what they had seen a few months earlier, and then also can they extrapolate to what happens when it's 1/4 of the way in. Let me show you some of the answers we got. 24% of the students give the right answer, 20 and 0 and 15 and 5, and mentions the concept of torque, which is precisely what we were after. Another 38% also gives the correct answer, but they don't mention torque. They give proportional reasoning, so it's not 100% sure whether they understand the underlying concept just from the answer to this question. Right, because they had to select an answer and then to type in their reasoning. 20% of the students says it's independent of the position. Doesn't matter where you put it. 10 and 10. That was precisely the misconception that we were trying to eliminate. 20% of the students at the end of the course still has that misconception. Those must be the students who did not see the demo, right? Well, actually, no, it's not that easy. In fact, there were a number of students who wrote, as shown in lecture, it doesn't make any difference where the block is put. The plank and the block form one unit, and the plank evens out the load. Hello, that was just what we're trying to disprove. Here's a student that, as shown in lecture, I was so excited. I thought, I have discovered a new psychological effect. I have some friends in the psychology department, so I went over to one of my friends in visual cognition, and I said I was really excited, and he asked me, what is it that you've found? And I described it. He patted me on the back. He said, Eric, we've known this all along. I said, really? Yes. Why do you like physics? He asked me. I said, well, I like physics because I don't have to remember that much. I can, trust my reasoning skills. He said, exactly. The brain does not store facts. It stores models. Now imagine you're one of these students who is thinking it doesn't matter where the block is put. It's on the plank in the middle. Now you come to class. The professor does a demo, takes that block, moves it to the side, and whoa, contrary to your beliefs, one scale goes up and the other goes down. You have what Piaget calls a cognitive dissonance. Now, before you have time to think about this cognitive dissonance, what happens? The professor continues to talk. Maybe you quickly jot it down in your notebook, but you have no time to adjust your model, your mental model, to the observation. And what happens is something that psychologists have indeed known for a long time. Instead of adjusting your way of reasoning to your observation, you adjust your memory to your faulty model. Advertising agencies, magicians, lawyers, politicians, they all do it continuously, right? Put the wrong model in people's head, they'll adjust their memory, right? So let's look at the data. Well, first of all, let me end with these data here. 10% of the students gives qualitative reasoning, so they don't give answers, they say larger or smaller. And then 6%, the forces are not balanced. So if you add the two numbers, it's all of a sudden more than or less than 20. And 2% are other incorrect answers. So now let's divide correct and incorrect. And I'm being very stringent here and only taking the ones who mention the right numbers and torque as correct, and see how it's distributed over those four modes, the four treatment groups. There it is, correct, incorrect, adding up to 100. But I want to draw your attention to those who have just observed. For this particular demo, they're lower than any of the other groups. In other words, is just observing harmful, right? But think about that one student who said, as shown in lecture, and then gives the wrong answer, right? Now, that student is even more convinced that his or her faulty model is correct because he or she has adjusted the memory to the wrong model. So we've rubbed it in the wrong way. Here's the exam question. This involves a little bit of physics, I'm sorry, but for the scientist among you, it might be fun to see it. So here we have exactly the same question, but in a totally different concept. Instead of scales, there are two ropes, and the tension in one rope is given, 150 Newton. Since the thing is symmetric, that tells you the other rope also has to have 150 Newton, which means that the weight of the plank is 300 Newton. But the question is, what happens if we move that rope that's at Q to R to the tensions in the two ropes? So if you understand the concepts, you see that this is really the same question as the other one. If you don't, this looks like something completely different. There's no relationship between the two. Now, 36% of the students give the right numbers, was the right answer. 13% of the students, the tensions don't even add up to 300 anymore. And the reason here is that, for those of you who know about torques, they took incorrect lever arms. So they basically plugged through the equations, but incorrectly applied them, which means there's a problem at the conceptual level, really. And then a fair number of students, 16 on the left and 2 on the right, I graded this problem because I wanted to see. I mean, I was doing the research. I was really curious. Came up with really weird numbers. How many of you are in science or engineering here? Can I see a show of hands? Okay, good. Because I want to see if you can figure out where these numbers come from. 112.5, 187.5. I mean, first one student and then another one and another one. Fairly quickly, I figured out that 112.5 is 3/8 of 300 Newton, and 187.5 is 5/8. But I had no clue where these 3/8 and 5/8 were coming from. You know, and then soon there was 10 students who had done this. And then finally there was one student who actually articulated where the 5/8 and 3/8 came from. I would never have imagined. Before I tell you, I'd let you guess. It shows what Steven Pinker calls the curse of knowledge. And once you know something, it's extremely hard to think like a beginning learner. You no longer can imagine the ways that students can go wrong, which actually is one of the reasons it's so hard to teach beginning learners. And it's probably also one of the reasons that peer instruction works, because students don't have that curse of knowledge. So where does the 3/8 and 5/8 come from?
Prior example.
No, not a prior example. Are you a scientist? Yeah. Good, very good. I was going to ask the other people in the audience to help out, but it's very good. Look at this. Imagine splitting the Planck in two between the points P and R, right? So this is 3/8 of the Planck. Here you have 3/8 plus a quarter, which is 5/8. So this rope basically supports half of the Planck between plus that, which is 5/8, and this supports just 3/8. And there, of course, 2 students thought, well, RQ sticks out. That doesn't need to be supported anymore. Who would have thought, right? Normally, when I used to grade exams, I would go through the solution and say, this is right. And when something went wrong, I would say, this is wrong, and stop looking at it, stop thinking about it. I've learned now that you can learn a lot by observing and documenting the mistakes that the students make. In fact, and this comes back again to your excellent question, you know, you can design good questions around the mistakes that the students make. Because you elicit these mistakes, and then you can confront them and help resolve the incorrect thinking. If you take the aggregate of all the demos that we did, you find that that observed group doesn't stand out as much as it did in the one. And you can see that the percentage of correct answer goes up, but not dramatically. Although the reasoning goes up very significantly and correlates very strongly with the increase in interactivity in the doing of the demonstration. Here are, this is the Planck. Here's the aggregate result for all. These are 7, eventually we did 12, but you can see that the ability to predict the outcome goes up, and the ability to reasoning and give the correct reasoning goes up too. So if we use the no demo as a control group and we measure the others against the no demo, we see that observe has a little statistical significant increase, which goes up with increased interactivity. It's much more dramatic if you actually look at the explanation rather than just the answer, because you see that a number of students give the right answer without being able to articulate their reasoning coherently, and I think that should be a requirement. You also see that the discuss is only a marginal improvement over predict, even though it has 6-minute extra time investment. So I think the conclusion for this is that demonstrations without engagement, and engagement meaning, you know, active engagement rather than just entertainment type of engagement, are just not very helpful. It can even rub in the wrong answers. And that the results can be improved dramatically just by having the students predict the outcome before they see it. That just takes 2 minutes. Give them 2 minutes to think about it before they see it. Then it makes the cognitive dissonance so much stronger that they'll be primed to think about it and actually revise their incorrect model. Okay, I have 20 minutes left, but I want to leave some time for discussion. So let me go to this last subject, which I think I have not yet published. And I think it's a very important point. Typically, we are praised for giving clear lectures. I would be very surprised if the end of semester evaluation at UT Austin does not contain the sentence, Professor ABC gives clear lectures, and then on a Likert scale. I see several people of you shake your head. Is that question still there? No? In engineering, not. Oh, it's not a campus-wide form. Okay. But in other courses it is. At Harvard, it still is. Professor Mazur gives clear lectures. Strangely enough, I never give any lectures anymore, and I get high scores on that question. And, you know, in general, confusion is considered to be something that is very discouraging, right? Oh, I'm confused, I don't understand. Smaller children have no problem being confused. They'll just continue to ask why. But as students get to middle school, high school, and college, confusion brings more and more discomfort. Why is that? I've only recently realized why that is. I think. I'm working on it, and I'm developing a new talk on that subject. Why is it?
We discourage the question.
How do we discourage the question?
Well, what do you think it is? Demand the answer from them rather than answering them.
That's part of it. We get impatient with the whys, right? But there's another, I think, equally important reason.
I ought to be understanding this better by now.
I ought to be understanding better, but why?
They're thinking.
There?
They're thinking and conflicting.
But it puts yourself in the shoes of a student.
They don't want to be embarrassed.
You get only rewarded for correct answers. Our approach to assessment punishes failures, punishes mistakes. Think about any creative or innovative process. It requires making mistakes. It requires failures. There's no innovation, no creativity without many more failures than there are correct answers. Well, our approach to assessment discourages failures, but it also discourages, it makes you very uncomfortable when you're confused. You have to have it right on the test, right? So confusion is a very discouraging feeling to most students. My rallying cry for 2013 is, assessment is the silent killer of educational innovation. Think of it. Whatever we do in the classroom, I realized last year, and I should have realized this much earlier, whatever you do in the classroom is irrelevant if you don't change the assessment, because students don't study to learn. They study to pass the assessment. Anyway, that's the subject for next time I come to UT Austin. So confusion is discouraging, but as we all know, to wonder is to begin to understand. We don't learn by just taking in the information. We learn by wondering, by saying, I'm wondering about this. Then, of course, you have to resolve that and have this aha moment. Oh, now I get it, right? And then you've basically internalized the concept of or the information. So the question I'd like to pose here for this last little part is, does confusion indicate lack of understanding? Or more precisely, conversely in a sense, does lack of confusion indicate understanding? When I gave my lectures, everything was clear. Students took notes, they walked away happy, they praised me for my clear lectures. Then I switched to peer instruction. I ask them a question, they think about it, they talk about it, they vote again. And now all of a sudden there are lots of questions. But Professor Mazur, what if this? What if that? Questions I never got before. I'm confused about this. It'd be very easy to interpret those signs as having done something wrong. But I know that the students learn more from the results of the FCI. That's why I asked myself that question. Now, we use a technique called just-in-time teaching. www.jit.org is where you can find more about it, which basically primes the students to come to class prepared. They have to either read something or watch something, and then they have a web-based assignment which is due the day before class. 2 questions deal with the content, and they're difficult. And 1 question is a feedback question. It's always the same. Please tell me what you found difficult or confusing. If you did not find anything difficult or confusing, tell me what you found most interesting. The last part is there so that I can't just write down everything is clear. Right? If everything is clear, you have to say what's interesting. I built a website where I could basically very quickly get those data, where I have the picture of the student, the name of the students, and what they found difficult or confusing. So it connects the response to the identity of the students. And what I found out was, anecdotally at first, was that there seemed to be an anti-correlation. There were some students say nothing is confusing, and I'd look at the student and think, this is not one of the better students in my class. And I clicked on the picture to get the data of the students, and indeed, this was one of the bottom performers. And then another student who said, I'm confused about this and about that, and a whole list of things. Oh, wait a minute, this is one of the better students in my class. So I decided to see what the correlation was between students' perceived confusion and their performance on the first question. So analyze the understanding and the confusion. I'm going to give you 1 example, and I'm taking here a chapter out of a standard textbook that they had read, and I'm showing you the 3 questions. This is on fluid statics. And this is a pre-med class. Fluids are very important, and in fact, the subjects that are discussed had to do with capillary veins, and the textbook that I had used made a very tight connection between medicine and the life sciences and the physics. Consider the capillary rise of a liquid in a glass tube. How does the pressure at point P here at the surface compare to a point at equal height inside the tube? That was question 1. Question 2 is 2 identical balloons are connected to a tube as shown below. Balloon B is inflated more than balloon A. Which way does the air flow when the valve P is opened? This is actually something I do as a demonstration. It's very counterintuitive. What happens is that the small balloon empties out in the big balloon. You may think that how can that be true, right? But I'm sure you've blown up balloons for birthday parties of kids. Imagine taking the balloon out of the bag, blowing it. You may have noticed that it takes a lot more effort to put in the first few breaths of air when the balloon is still flat. You have to really blow hard. Once there's air in it, it's a lot easier. The reason is that when the balloon is not very inflated, the curvature of that membrane is very round, so it pulls in. As it gets bigger and bigger, the elasticity is in a direction that is not inward as much as when it's less. So the elasticity basically doesn't do it. This is very important in medicine. The reason babies born before 20 weeks of gestation have, low survival chances is because the lungs, which have alveoli, which are basically little balloons inside the lungs, don't have a liquid called a surfactant, which reduces, if you want, the surface tension or the surface elasticity of these alveoli. And what happens then, in the absence of that surfactant, is that as soon as air comes in, the little alveoli collapse into bigger ones, causing rupture and therefore death. After 22 weeks or 20 weeks of gestation, the body develops the ability to have that surfactance which coats the inside of the alveoli, equalizing the pressure between alveoli of different size. So it's, and the book actually mentioned that. Now, the students are not evaluated for the purpose of their grade on the correctness of answers 1 and 2. They just have to put in the effort. I tell them, you have to show me that you've done the reading. But even if you get it wrong, it's okay. Question number 3, please tell us briefly what points of the reading you found most difficult or confusing. If you did not find any part of it difficult or confusing, tell us what parts you found most interesting. Let me give you a sample answer. Capillary action is due to the cohesion between water molecules and the and the adhesion of water to the surface of a glass tube. This is a sentence that's just taken out of the textbook. Negative pressures can result from the cohesive forces of water. Another sentence picked up. I don't know what the logic here is, but the student just took two sentences. They're both correct. They're out of the book. But what the relationship is, I don't know. At the same height, the pressure inside the tube is much less due to negative pressures. Sorry, that's wrong. The air flows from high pressure to low pressure. That's correct. The fully blown up balloon has higher pressure, than the half blown up balloon. So the air flows from the fully blown balloon to the half filled balloon. Both questions wrong. Now look at the third question. Nothing was difficult or confusing. The sections on the surfactants in the lung and the heart as a pump were interesting because they relate physics to biology. So here I'm going to show you, now I'm going to show you a totally different answer from another student. The water rises because of an interaction between the water and the walls of the tube. This is the same as that first sentence from the other student, but instead of using the terminology from the book, the students had recast this in his or her own words. This interaction creates an upward force which causes the water to rise. That's the negative pressure here. The force is due to surface tension between the water and the walls of the tube. The pressure at the point inside the tube must be the same as the pressure at the point of equal height outside the tube, because if there was a pressure difference, then there would be a net flow of water in or out of the tube until the pressure was equalized. Fantastic. Correct reasoning, well articulated, everything. Second question. Laplace's law tells us that it requires a greater pressure differential to maintain a small sphere than a larger one. That's right. So the pressure in the small balloon must be greater, and the air will flow from the small balloon into the large one. Great. Now look at the third question. I found the explanation of Laplace's law to be inadequate. And while I can understand the conclusion drawn, I don't understand the reasoning which led to the conclusion. Okay, so I decided to do a more systematic analysis. Let's code question 1 and 2 on whether they're correct or incorrect, and then question 3 on whether there's confusion expressed on the topic of Q1 or Q2. So this student would be right, not confused about capillarity, but confused about Laplace's law. This student here, the previous one, wrong, not confused about anything. Okay, so let's see what the correlation is. Of the students who said that they were confused about capillarity, 44% got the right answer. Of the ones who said they were confused about Laplace's law, 49%. But now look at the students who did not express confusion. In both cases, fewer correct answers. In other words, the confused students are twice as likely to be correct. Shortly after I did this, I switched to a different text, a text that actually was focused on eliciting students' confusion during the reading. And that's the text I've been sticking to, unfortunately, which means it's hard to go back to the other one. And then that difference goes away. It goes away. So what does this mean? Because it basically compels them to think while they're reading. Right? Whereas in the other book, they were just reading it like a novel. It was going into the brain, and maybe, it was the highlighter. They would highlight a few things, but there was no real assimilation of the concepts. So what does this mean? This means there tends to be more confusion about the students who are beginning to learn. It's actually not that strange if you stop to think about it. Because confusion is actually part of the learning process. It's a necessary step. And in our standards approach to teaching, we're sort of shoving it under the rug. We're trying to avoid it by painting the illusion, by giving students the illusion of clarity, and not even giving them a chance to develop that confusion. I think this is really important, because I think this is a potential barrier to change in education. Because what does this mean? This means if you compel your students to work harder on developing the ideas in and outside the classroom, you will not have fewer confused students. You will actually expose the confusion. And both you and your students may misinterpret that, right? I mean, I can see my students, and in fact this happened, come to me and say, Professor Mazur, you confuse me. Your lectures are confusing. In fact, on the evaluation, it could have a negative impact. So I skipped a slide here. So I hope that with these 3 examples, I've given you an idea of how important it is to collect data. In a sense, I see my classroom as an extension to my laboratory. I will not fail to use my classroom as a laboratory for educational data and as an opportunity to improve my approach to teaching. Just as I collect data in my lab on the interaction of light and matter, well, in the classroom, I collect data on the interaction of words and students, so to speak. And I think it's vital to improving our education. I encourage you to be scientific about your approach to teaching. A long list of people I should acknowledge. If you're interested in a copy of this presentation, you can go to the, no need, I see a lot of people writing it down. No need to write it down. Just go to Google, enter my last name, M-A-Z-U-R, and then hit this I'm feeling lucky button, and you'll have a copy of the presentation. Thank you very much. Do you want to do a demonstration? Okay. Yes?
2 questions. One is, which text did the students like better? And the second one was, how do you confuse students downgrade course instructor evaluate, numbers that were all evaluated on the regions look at, and promotions are based on?
Yeah. So 2 things. One, which text do the students like better? And the second one is, do students who are confused downgrade the evaluation of the teachers? Unfortunately, I would love to have the answer to that second question. But I have a major problem. I only get aggregate results of the end of semester evaluation. They're anonymous, so I don't know. I cannot correlate the students. So I have no idea. No idea. I would love to know. I think it's important to know, but there's no way I can get access to it. In terms of which text do the students prefer, I have not been able to really study that, because when I did this, when I started implementing JIT, I was using my own text, which has all of these questions built into the text, forcing the students to think for part of the course, and I used this other textbook, Sternheim and King, in case you're interested, for a number of chapters that I had not yet written. And so at the end of the evaluation, again, we didn't ask them question, do you like this better or that? So unfortunately, I don't have the answer.
How do they do in their next physics courses compared to your previous?
How do they do in the next physics course compared to previous courses? Remember, these are non-majors. So they're students who, they're either engineering students or they are.
How do they do in their engineering course? Do you have any idea?
I never collected data on that. So do we know of data that have been?
For subsequent classes?
Yeah.
We have the retention data.
Yeah, okay, so one thing that is really interesting, but it doesn't really address your question, which Julie pointed out here, is that we have a significantly larger retention of students in STEM disciplines. For years, I asked students, and I get them in their, first few years at Harvard, to write down what their intended major is. After 15 years of data taking, I thought, oh, the registrar knows things that we don't know, and I know things that the registrar doesn't know. I'd analyzed gender, but I thought it might be interesting to look at other minority status, to look at SAT scores, and so on. So we went to the registrar, and we said, let's merge the 2 databases and then see if we can get additional data. One of the first things that stood out is that the major in which the students had, the concentration in which the students had actually graduated, differed from what they told me. And I found that before I switched to peer instruction, about 10 to 15% of the students dropped out of STEM disciplines. So they thought they were going to major in mathematics, engineering, or sciences, but then eventually they majored in something very different. After I used peer instruction, that dropout rate was reduced by a factor of 2. A similar study was done also at a community college, very different population of students, which found a very similar trend. But there they didn't look at dropout rates of the major, they looked at dropout rates from the course. So in other words, how does the population who does the final exam differ from that on the first few weeks of class? Very significant reduction in dropout rate. Unfortunately, it doesn't address the actual question you asked, which I don't know the answer to. Let's see, somebody who has not yet had it.
I have a question. We're really encouraged to post all of our exams and change our exam from one semester to the next, because there's fraternities that have banks of questions. And if you're looking for consistency across a big data set or semesters, how can you write an exam, especially in a discipline that's a little less black and white than sciences, to get that consistent data?
So the question is, we're forced to post the exams. How can you, if previous exams are accessible, look at longitudinal data from year to year? I also post my last 3 years of exams. Fortunately, I can often dig back further back in time. I also more recently decouple the data I use to analyze the learning from the assessment that factors into the grade. I mean, in an ideal world, the two are, of course, the same. But as my data, I think, has shown over and over ago, that's not necessarily true. Students might be able to solve traditional textbook problems, but do poorly on the FCI. It is a problem, but you may want to think about having an additional assessment which you sell to your student as an opportunity to practice their knowledge, which gives you an opportunity to collect data that you will not have to put on the web, and you can use that year after year. And because it's low stakes, students will not be compelled to sharing it with students in future years. And it could give you very valuable data. So I think there are ways around it. Also, I really think we should get away more and more from summative assessment and go more and more towards formative assessment. I recently read an article by Paul Black called Inside the Black Box, Working Inside the Black Box. You can Google those terms. And he refers to, basically his goal is to use assessment for learning rather than for ranking and classifying students. If you stop to think about it, most assessment in both secondary education and higher education are focused on classifying and ranking, which is very stressful to students. I mean, you might remember your own stress. And a study that was done in the UK, a fairly large-scale study, showed that if you take away the classifying and the ranking, you take away the grade, and you focus the assessment completely on the other important task of assessment, namely feedback to the learner, students actually work harder and better. They're freed from this pressure. Well, we put so much weight on a cumulative final exam. What do students end up doing? They end up cramming. Goes only in short-term memory. They just study so as to pass the test. They don't study because they have this innate desire to learn. We've taken away the innate desire because we've replaced it with this high-stakes testing. There's so much talk about it. I think high-stakes testing should be forbidden, frankly, because it's not conducive to learning. An anecdote that made that vividly clear to me happened a year ago. I was taking a flight to Buenos Aires from Newark. Sat down in my seat. Next to me sat a young woman who had just obtained her degree from the University of Chicago. I started talking, and she said she was working for a cloud-based education company. I have a cloud-based education company, so I thought I better find out what she does. So we started talking, and it turns out her company was doing flashcards for smartphones. I did not really roll my eyes, but I felt like rolling my eyes. I'd just gone to a talk by Reddy Rödinger, a psychologist at Washington University in St. Louis. And I don't know how many of you have read his paper on practice retrieval in Science in 2010, but he showed that if you study with flashcards without doing it the standard way, you basically remember things well for a very short term, but after a week, students only remember 35%. I downloaded his paper on my iPad, so I thought, I told her, do you know that if you study with flashcards, you only remember things for less than a week, and after a week, 65% is gone. I grabbed my iPad, pulled up Ready Runninger's article, and I gave her my iPad. She looked at it, skimmed the abstract, gave my iPad back, looked me straight in the face, and said, "But we only guarantee that they will pass the test." Wow, I had never thought about it that way. I had never thought about it that way. You know, the assessment is what really drives our students' behavior. So I'm sorry that I'm drifting away from your original question, but I really think that we should revise our assessment strategies. I think it's crucially important.
Yeah, how easy or difficult it is to convince other professors at Harvard or elsewhere to do this flipped classroom teaching, not lecture?
How difficult is it to convince other professors at Harvard and elsewhere to do this flipped approach to classroom teaching? Very difficult. It is like moving a mountain. And at Harvard, it's impossible. But now, in all fairness, there's quite a few of my colleagues who have changed their approach to teaching. But it's not because of what I did directly. I mean, we don't have a culture where we learn from each other, talk to each other, you know, the same way we have a culture to learn from each other in our own disciplines. Right? It's rare to have a talk or a regular activity where faculty exchange ideas about teaching. My own faculty changed their approach to teaching not because they observed me in my classroom. No, I'd get invited to Stanford or another school and talk about my teaching there, and then the faculty at Stanford would change their approach to teaching because they thought we at Harvard were teaching differently. And then half a year later, one of my colleagues would go to Stanford and give a talk on his work there and hear, "Oh, in our introductory classes, we're using your colleague Mazur's method. What is he doing?" Yeah. So basically, the message went from me to others, but it's taken over 20 years. Maybe one more question? I mean, I don't know what your time is. 2 more questions. Okay. You've had your hand up.
Well, I actually had two. First is, our classrooms are not designed for students to interact very well, all the linear seating. And maybe you can get 2, possibly 3, together. Does it make a difference if you have bigger groups or not?
So shall I take that question first?
Okay, yeah.
So the architecture of a learning space, the question is about the design of the classroom, which is not conducive to interaction, right? And the architecture of our learning spaces is really dating back to the invention of the amphitheater by the Greek. And they did not develop that for teaching purposes. They developed that purely for performance purposes, which is why so many professors become good performers, I guess. But you're right. When you sit in an audience or in an auditorium like this, even here right now, you're automatically put in a passive role. Right? Your expectation when you sat down in this room an hour and a half ago was, I'm going to sit here and observe. And most of our classrooms are designed like that. That picture that I showed in the beginning of me teaching, it focuses the attention of all of your students on the instructor. The instructor is active, and the expectation is that the audience is passive. You can ask, the nice thing I think about peer instruction is that you can cope with an ill-designed learning space. Because suppose that I'd asked you to turn to your neighbor, well, you happen to sit on the aisle, so there's only a person on one side of you, but you could also turn to the person behind you, or maybe if the person in front of you turns back. So you can still get, on average, maybe somewhere between 2 and 5 people to talk together. If the group is too large, the method doesn't work because there are too few people who can talk, right? So typically you don't want groups much larger than 2 or 3 or maybe 4 students. So the good thing about peer instruction is you can use it in ill-designed learning spaces. Ideally, however, we do rethink our spaces because they should not be instructor-focused, they should be student-focused. A much better arrangement would be round tables with small groups of students. Yes, half the students will have their back to you, but that's a good thing because they should be focusing on each other, not on the teacher. I know you had another question.
It's okay. I remember way back, it was sort of enlightening for me reading a little biochemistry book, and I read through the chapter and I couldn't answer a single question, which is to say I was familiar with everything, and that was deceptive. so it raises this question, because I love what you said about confusion. You know, about clarity and then students deceiving themselves through their sense of familiarity versus writing another way, sort of bringing this into the textbook and changing the model of the book is what I'm asking.
Yeah, so I don't know how I should summarize your question, but basically we all have the experience of reading a book and everything being completely clear, and then discovering much later it isn't clear. I would like, the reason I'm thumbing through my slides here is because I want to get back to this slide here, because in a sense what happens when we read superficially, right, or when we fast without pausing and think, is the same thing as happens in the classroom, right? Our brains are not engaged. We're not actually processing the information. Just goes. Somebody has once described the lecture as a process whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either, right? And we have to try to develop the opportunities for students to actually not just take in the information and then learn to regurgitate it on the examination, but to actually take the information and build mental models, think about it, right? So and it's deceptive, right? Because I mean, I'm sure that the students who went to these classes and had their brains essentially turned off might have been very happy with those classes, right? These classes here, very happy. They seemed clear, but they only seemed clear because they had not elicited any confusion or any thinking. So, thank you. One more, one last question. Okay, all the way in the back there.
Thanks. What are your thoughts on using this approach when teaching something like writing and language arts, where maybe there isn't one right answer, and also your students each have their own needs and problems, and even peer editing has limitations because the students don't always take it seriously. They may not be able to give adequate feedback.
Yeah. So what are my thoughts about using this approach to teaching in languages, arts, and humanities? I think any discipline that requires critical thinking, which means anything we teach in higher education really, lends itself well to this. Any subject that is merely memorization of information or rote application of procedures does not lend itself for this. But I would say that's exactly what we don't want to do. We don't want to teach memorization. We don't want to apply rote memorization. So let's go to literature, for example, right? In literature, yes, you might not have an answer that's right or wrong. Let's say you read some kind of a passage. The interpretation of that passage, even scholars might not agree on what the exact meaning is, and the author might be long dead, or even if the author is living, he or she might not be willing to disclose the actual meaning of the passage. So we could approach the teaching in two different ways. We could say, here's this passage, this is one interpretation, that's another one. Or we can ask the students to form their own interpretations and then defend them against each other. By doing that, I think we teach the students of independently coming up with their own interpretations rather than accepting interpretations from scholars, which is, I think, part of critical reasoning. So I think that the method works equally well in your field, which I assume to be language, as it does in my field. Good. Okay.
Thank you again, Dr. Mazur.
Oh, please. No doctor.
I can't think of a better example of how data can really inform what we do, not just on a classroom level, but on a program level and on an institutional level. And what we really wanted to do today is just give you a quick teaser for the Making Decisions with Data website. This is an online resource sponsored by the Texas Higher Education Coordinating Board and developed by a team of scholars here at UT with assistance from scholars around the country to really bring home this concept of going from a moment of wonder and how we can use data to move from a moment of wonder to a moment of decision. and how that can impact what we're doing in our classrooms, in our programs, and in our institutions. Tomorrow, you'll have an opportunity to peruse the site, which includes videos, online activities, assessments, and 5 different modules to really guide you through a process. We hope you'll take advantage of this opportunity, and I wish to extend my thanks to the Texas Higher Education Coordinating Board for sponsoring this work. My thanks to all of you for your interest. My special thanks to Dr. Mazur for being here with us today. And my thanks especially to the Making Decisions with Data development team, many of whom are standing here in the back today. Thanks very much for all of your assistance and for sharing your time with us today. And hook 'em horns.